Welcome students. So we are going to discuss about rate of change in natural and social sciences. We have already seen the derivative as a rate of change, and we want to apply the concept of derivative in natural and social sciences. So let's look at the first example, which comes from the physics. The equation of motion of a particle is given by this formula. S of t is 2t squared 2t cube minus 3t square minus 12t for t greater than equal to 0, where s is measured in meters and t is measured in seconds. So first we need to find out, so the first problem tells us to find velocity and acceleration of the function. The second problem is asking us to sketch or graph the position, velocity, and acceleration for t in this range. Third problem is asking us when is the particle speeding up, and D, what is expression for S triple prime, which is derivative of acceleration represents. Okay. So let's embark on this. So first thing, so we know that velocity is a derivative of the position. So we have V of t is S prime t, and that is derivative of 2t cube is now 3 times 2 times 3t square, which is 6t square, again minus 6t minus 12. And we know the acceleration is derivative of velocity, and that is going to be 12t minus 6. So here we have expressed that velocity and acceleration as a function of t. Now we want to sketch the position, velocity, and acceleration for time t between 0 and 5. So this S of t represents your position, and we want to first draw V of t. So to draw V of t, we are drawing derivative of this function. So note that here the derivative of function is 0. So here the slope is equals to 0. So at this point, your velocity will cut x-axis. Now, so your velocity, and you can see that somewhere here it's going from concave up to concave down. So that means your velocity is going to change direction here. So let's draw this. So at this point, so the function is decreasing here. So that means the velocity will be negative in that case. So it's going to be roughly, again, we are drawing a rough sketch of it. And after this point, the velocity starts increasing. That means the velocity will be positive. So when I join this, this is how the graph. This is what I get for V of t. Now for acceleration, which is derivative of velocity, how do we go about it? So acceleration is derivative of velocity. So again, we have to see where does this becomes 0. So here the slope is 0. Before that the function is decreasing, after that the function is increasing. So you'll see that acceleration before this value will be in, before this value is going to be negative, and after that it will be positive. So this is just drawing it from the graph, all right? But we can draw it better from the expression of it. Namely, notice that we have 6t squared minus 6t minus 12. And if you look at the vertex of this, minus 4 times, so minus 12 by 12 minus 3 by 2, which is going to be 12 minus, so this 12 minus 1.5 is going to be 13.5. So when you draw it like this, you can really see that somewhere around 13, so let me draw this again. So somewhere around 13, which is here, you will have the vertex. So 13 half and 13, and then we already see that it's going to be cut the axis at this point. So this is how the graph looks like. Okay, so this is drawing it algebraically. Similarly, we need to draw the acceleration. So acceleration is a linear equation. So you'll see that acceleration is a linear equation passing through, it will cut t-axis when you get t equals to half. So it will cut t-axis. And then when you draw it, this is how it looks like. It's a straight line. So let's look at another point for it. When t equals to 0, we have minus 6. So t is 0, it's going to be minus 6. So somewhere around here. So this is how your acceleration looks like, roughly. So this is the a of t. So of course, when you use algebra, you can draw it more or less precisely. So these are the graphs of velocity, acceleration, getting out of position vector. Now the next question is, so what does it means that what does it mean? So when is the particle speeding up and when is the particle speeding down? So particle speeds up when v of t times a of t is greater than 0. That means velocity and acceleration both have positive sign. Sorry, both have same sign. Yeah, that is non-zero. Both v of t and a of t have same sign. So what about, so let's see, what is the 0 of this guy? So when is v of t 0? So we have to see v of t equals to 0 when we have what? When we have t equals to, so when you solve this, you get when 6t squared minus t minus 2 equals to 0, this implies t minus 2, t minus 2 times t plus 1 equals to 0. This means t equals to 2. Since t equals to minus 1 is not a possibility. Okay. So this is what we get for when t is 0. Now What about a equals to 0? So a is 0 when t equals to 1 over 2. So now we need to decide. So we said the particle speeds up when v of t times a of t is greater than 0. So we need to investigate that case. When is v of t, a of t greater than 0 times a of t greater than 0? So let's mark these points here. So I'll draw a straight line, mark where they are becoming zeros. So when is v of t becoming 0? V of t is becoming 0 at 2, and a of t is becoming 0 at half. Now, what we need to do is we need to see what is happening in this interval. What is the sign of velocity and acceleration? So in this interval, v of t, let's see. So v of t is positive. So v of t is this equation here. So 6 times, so I could have written here 6 times t minus 2 t plus 1. So let's take a value here, any value in this range. So let's take 1 by 4. So if you put 1 by 4 in this one, you'll get negative. Here, when you put 1 by 4 in this part, you'll get positive. So positive times negative is negative. So v of t is negative in this part. What about a of t? A of t, either you can see from the diagram or you can check that a of t is going to be negative here. Similarly, in the other part, what do we get? We get from minus half to 2, let's take 1. Or you can see from the graph as well. Between minus half and 1, between half and 1, which is here, what is happening to the velocity and acceleration? So again, velocity is still negative. Sorry, here acceleration is also negative. So negative makes it positive, right? Now here you will see that V on this part, in this part acceleration is positive, velocity is negative. So we can write velocity is negative and acceleration. So velocity is negative and acceleration is positive. Now we are at this point 2. After 2, both, so velocity is positive and acceleration is also positive. So velocity is positive, acceleration is positive. So when both of them have same sign, the particle speeds up when v of t times a of t is greater than 0. So therefore we can write down particle speeds up in what range? When v of t times a of t is greater than 0, that is in what interval? 0 to 1 by 2. And let's keep this open intervals. And also it speeds up from 2 to, now we have restriction on our domain, we have to go from to 5. So we'll say particle speeds up from this to 5. Okay. Now when does particle speeds down? When v of t times a of t is less than 0. That is, we get on what interval? Half to, because that's where the signs are negative. Okay, so this takes care of the thing. Now, what is the third derivative of position, which is the derivative of acceleration? So derivative of acceleration basically represents a sudden change in acceleration. So when there is a sudden change in acceleration, you feel a jerk. So, right, you feel like your car, you feel like a kind of a jerk motion. So A prime t is called, rightfully called, jerk. Yeah, it represents change in acceleration. Okay, so that was the example from physics on how to use the derivative to understand the motion of particle and velocity and acceleration. Yeah. Now the next example comes from the chemistry. So let's read this problem and make sense of it. So if one molecule of C is formed by one molecule of reactant A and one molecule of reactant B, and initial concentration of A and B have, so we should have basically, before we go further, we should have written the units here. So this will be meter per second square, and this will be meter per second. Yeah, it's important to write down the units. Okay, so if one molecule of C is formed from one molecule of reactant A and one molecule of reactant B, and initial concentration of A and B have common values. So A and B are A moles per liter, then C is given by the following formula. So this is your formula for C, A square KT by AKT plus 1, where K is a constant. Is asking find the rate of reaction at time t. So what is the rate of reaction? So rate of reaction is going to be at what rate is the reaction happening. But reaction happening is same as how fast is the molecule is forming for C. That indicates the rate of reaction, right? So we want to find out, so for A, we need to find out dC by dt. That is going to be d by dt of A square kt over AKT plus 1. Now we can apply quotient rule. So let's apply quotient rule here. So we get AKT plus 1 the whole square, AKT plus 1 as it is, multiplied by derivative of numerator, which is going to be A square K minus A square KT times derivative of denominator, which is going to be AK. Now you can see that you can cancel off AKT times A square K, which is going to be A cube KT, which is what you're going to get here as well. So the answer turns out to be A square K over AKT plus 1 the whole square. Now, what about B? Now, so this is the rate of reaction. So if we represent X equals to C, show that dx by dt square equals to K times A minus X the whole square. So we are representing X equals to C, so we need to compute dx by dt, which we have already computed. So dx by dt is A square K plus AKT plus 1 the whole square. But now we want to show that this is equal to k times a minus x square. So we want to take k common. We have a square akt plus 1 the whole square here, and we want to show that this part is equal to a minus x square. So how do we do that? So one way is to compute a minus x square on side and show that it is equal to this part inside, or rearrange it to make it look like that. So this is going to be, so how do we do that? So either way, so let's choose a way to do this. So let's see. So we have k, we have a square akt. So let's write it as a square kt. So let's just work with left hand. So this is your left hand side. Let's work with our right hand side and show that it's also equal to this thing here. So right hand side is going to be k times a minus x the whole square, which is going to be k times a minus x, which is now you can basically see that this is going to be a. When you multiply it out, you get a square kt plus a minus a square kt divided by akt plus 1 the whole square. So these guys will cancel off. You'll be left with a, and when you square that, you get a square. You get a square, then this k will come out, multiply in, so you get this, and then you can keep it out if you want, akt plus 1 the whole square, which is your RHS. Now you see that left hand side and right hand side are equal, so this is same as LHS. Therefore, the equality follows. Okay. Now let's ask the following question. What happens to the concentration as t goes to infinity? So in this case, we have to take C limit as t goes to infinity of C. So that is same as limit as t goes to infinity of, what is an expression for C? A square kt divided by akt plus 1. So let's write that down. A square kt divided by akt plus 1. Now we need to simplify this. So limit as t goes to infinity. So either you can apply L'Hopital's rule, or in particular you can notice you can divide top and bottom by t. So you get a square k upon ak plus 1 over t. And as t goes to infinity, this goes to a square k by ak, which is a. So when reaction goes for long time, so what does it mean when reaction goes for long time? A long time, C approaches A moles per liter. And it makes sense, right? Because why is that? Because think about it. You have A moles of this, A moles of chemical A or molecule A, and A moles of molecule B. Now, when you combine them, if you're combining each of the molecules to get one molecule of C, so at the end, if the reaction is going properly, all the molecules will be converted to AB molecules will be converted to 2 molecules of C, right? Okay. Now it's asking the next thing, what happens to the rate of reaction at T goes to infinity? So let's look at that. D. So we are asking what is limit as T goes to infinity of dC by dt. Because after all, dC by dt is the rate of reaction, right? So what happens to the rate of reaction? Now, if you think from the aspect of chemical reaction, what is happening is C is approaching A moles per liter. That means dC by dt will approach to 0, right? Because after eventually the reaction will stop after some time. So let's see if that's indeed the case. So limit as t goes to infinity of dC by dt. We already found out an expression for it. So we have a square k upon akt plus 1 the whole square. And now as you see, as t goes to infinity, the numerator is fixed, but the denominator is getting bigger and bigger. So it goes to 0. Yeah. So eventually, that is, eventually reaction stops as expected. So this is an application of rate of change in chemistry. So let's look at the next problem coming from economics. So suppose the cost in dollars for a company to produce X pairs of genes of new line of genes is Cx, which is 2x plus 3x plus 0.01x squared plus 0.0002x cubed. Find the marginal cost function. So what is the marginal cost function? So marginal means what is the cost of making one extra, all right, one unit, all right? So generally the marginal cost function is given by C of n plus 1 minus Cn. So what is the marginal cost? Marginal cost function is so let me just explain that. Marginal cost is an increase in cost, the total cost. Yeah, the cost is given by this formula here. So marginal cost is increase in cost that results from one unit increase in the output, right? In the output. Yeah. So you see here, you are having cost for producing n plus 1 is Cn plus 1. Cost for producing nth is Cn, and then the cost of producing that extra n plus 1th item is this one here. So let's compute what is Cn. So Cn plus 1 minus Cn. So we get Cn. So we have Cn is basically, so I'm subtracting these guys. So Cn is 2000 plus 3 times n plus 1 plus 0.01 times n plus 1 square plus 0.0002 times n plus 1 cube, and I have Cn, and I'm going to subtract them, right? Plus 3 times n plus 0 times 0.1 n square plus 0 times 0.002 n cube. Now when you subtract them, so marginal cost is going to be, when you subtract, so this will become 0, so you'll have, here you will have 3, you'll have 0.01 n plus 1 square minus n square, that is going to be 0.01 n plus 1 square minus n square, plus here you will have 0.0002 times n plus 1 cube minus n cube. So if you simplify this, this will be 3 plus 0.01 times 2n plus 1 plus 0.0002 3n square plus 3n plus 1. So this is your marginal cost function. Right, now B. So let's take B. So what is C prime x? So C prime x is going to be, when you take the derivative of that, it's going to be 2x. Sorry, derivative of 2000 is 0. 3 plus 0.02 x plus 0.0006 x squared. Now let's compute. So it's asking compute C prime of 100. So C prime of 100 is, when you put 100 here, you get 3 plus 2 plus 0.0006 times 1 4 zeros. So that will neutralize. So you'll get 3 plus 2 plus 6, which is going to be 11. So this is the, so C prime is, so C prime x is this guy here, and C prime of 100 is this. This is the cost of producing the next pair of genes. So C, compare C prime 100 with the cost of manufacturing 101 pair. So 101 pair, C of 101 pair would, of genes, so computing for finding how much it costs to make 101 pair, you will see that this is going to be this guy, and when you do the computation in this, you'll see that that's roughly 11.0702. So this is in dollars, this is also in dollars, right? So note that C prime of 100 predicted at what rate, how is the cost increasing at 100 unit, and C of marginal cost of 101 object is 11.0702. So you see they are roughly, so C of 101 minus C of 100 is roughly going to be, C prime of 100. So this is what economists do in computation, that instead of computing marginal cost this way, we take the derivative because it makes it easier for computational perspective, and they are approximately same. So there's no harm in replacing the marginal cost of 101th item with C prime of 100. So let's come back to another example. So another example of rate of change in, again, in real application. So a height of a certain cylinder is always twice the radius. So we have a cylinder. So So we have certain cylinder which looks like this. Okay. Now, if R is the radius and H is the height, this says that H is always 2R. Yeah, because it says that it's always twice the radius. If the radius is changing, show the rate of change of volume with respect to what? So rate of change is always measured with respect to. So with respect to R is equal to its surface area. So what are we asking? We are asking dV by, we want to know dV by dr. So dV by dr, and that is equal to the surface area. This is what we want to show. So first of all, what is surface area? Here. So surface area is, first of all, you have these surfaces, right? You have one circle on top and bottom. And then we have the side surface, which is the, okay. So let's write it down. So another surface is this part, right? So expression for, so notice that numerator, sorry, notice that top and bottom are circles, right? So top and bottom are circles. So surface area is going to be pi r square plus another pi r square. Now, if you basically cut it open, let's basically cut it open here. Let's just basically, then you will get okay, you will get the base will be 2 pi r, perimeter of base or circumference, and height is h. So the slant surface is going to be 2 pi r h. But we know h is always 2r, so this is going to be, we have, since h is 2r, this is going to be pi r square plus 2 pi r times r square, sorry, times 2r. We should write, since h equals to 2r always, this is going to be 2 pi r square plus 4 pi r square, which is going to be 6 pi r square. So this is the surface area. Now, what is the volume? Volume of a cylinder is pi r square h, which is going to be pi r square. H is 2r, right? We get pi 2 pi r cubed. So therefore, dV by dr is going to be d by dt of 2 pi r cubed, which is going to be what? 6 pi r square. So we are doing derivative with respect to r. So you see, which is equal to the surface area. So hence proved. So this is how we can apply the rate of change in social sciences.